polarity, when we have two atoms bonded together, if they are the same kind of element, like two CLs, then they share nicely. But if they're not the same kind of element, then every element has its own electronegativity. Electronegativity is how much atoms are pulling on bonded electrons. So the more electronegative element will pull more than the other one. And so I'll give you a moment to write this down. Would you mind sliding over one seat for us?
Yeah, sure.
So you can get more of a straight up view. Here's the person responsible for this excellent quality. Thank you, Vinny, for doing that.
Finally, your hair is brown again. I just noticed.
Wasn't it always?
Yeah, no, like last year you guys for swimming.
You just noticed?
No, I know, but you know, there's still.
He was sliding.
Okay.
Don't let that whole thing spill on the iPad.
Oh, no, I won't.
Okay.
I thought it was clean water, though. I'm kidding.
Those pictures actually make it so much easier.
Yeah.
I lost it all
Guess what we're studying in physics? Electrons.
Are you?
Yeah.
In AP physics? No, it's regular physics. What about
Physics with atoms.
Charges and electrons?
Oh, we're not there yet. There's four of them.
Wait, it's like R squared.
Starting electricity?
With the K, that's 9 times 10.
Yeah, but what else do you use?
With the K.
Yeah, it's like.
So is that the K for that? Oh no, the K is going to change because now the units are going to be like a plus or minus like 1.6 times 10 to the negative like something coulombs, right?
Mr. Morris is taking too long.
I don't know what you're talking about.
Okay, never mind. For Coulomb's law. Yeah.
Oh, and you know what the K is for Q1, Q2 over R?
Yeah. Well, but then that Q is Newton square over Newton Coulomb square over meter square. No, Newton meter square over Coulomb square. That's what it is. Yeah.
Yeah, there's no like basic
Well, it fits in. Okay. Now, to give you an analogy of the way that the polarity in bonds works, think of polarity as a tug of war. Both of the atoms are trying to get the electrons closer to themselves. Well, the one that's more electronegative is going to win, is going to get the electrons more toward itself. It doesn't necessarily rip the electron away, it just pulls it more closer to it than the other one. Think of it like this. You know LeBron James, right?
Yeah.
LeBron James, do you think of him as a strong person? Very strong, he is. Anyway, stop. Imagine LeBron James in a tug of war against Justin Bieber. I know there's always Justin Bieber fans, Mohammed, so that's good. I'm glad for you. Unfortunately, though, in this one, your guy is going to lose. And, I mean, you can see how LeBron is going to, it would be fun if they were really doing that and there was a mud pit for the loser to fall into. But the tug of war, of course, would be won by the stronger one. And if I could just, oops, sorry. Why is it not expanding? I just did it. Okay. This is an example of a polar molecule, or a polar bond, in which the chlorine is more electronegative than the hydrogen is. So the chlorine yanks the electrons toward itself, the shared electrons, that is. It's already got its own 6 there in lone pairs, and then it's got its own here sharing with the hydrogens here. So the chlorine is like it's taking hydrogen's electron away from it. So the chlorine has 8 electrons around it. Closer to it, that makes the chlorine partially negatively charged. See how there's a little sign there, it's a delta, it's lowercase delta. Delta negative means that this side of the molecule is negative. And where the electrons are being pulled from, this side of the molecule is positive. That's what a polar bond is about. If it's an ionic bond, that means that we have two things that have a huge difference in electronegativity. This is more like LeBron against Bieber, where I mean, there's not even a competition there, and the electron is really pretty much gone onto the chlorine.
You really hate him. It's not
He's
even
Canadian.
Say I hated
It's a
it.
fact. It's a fact. Everyone does.
He's Canadian.
Can you hold that down?
Bieber's fine.
Yeah,
He's
he's
an
great.
anti-Canadian. No,
Thank
wait.
you.
He's like the dark Canadian, like dark matter. He's the dark Canadian.
Prox, don't hate. Okay, now what this doesn't tell you is how do you know whether things are big polar bonds or not. I'm describing polar bonds with this and giving you examples, but how do we know if a bond is polar or not if you especially don't have the electronegativity values? Now, that's what causes polar bonds, is the differences in electronegativity. But what if you don't know what those values are? There's a general rule that we can use. Everybody good with that, Vinny? Did you catch up?
Yep.
If a bond contains fluorine, oxygen, nitrogen, or chlorine, FON and Cl, Fonkel, then it will be a polar bond. So the other example I had HCl. Well, that was H with a Cl. There's the Cl, so that makes a polar bond. These 4 molecules are the highest electronegativity of all elements. Yep, we do this. Should be a review, but it's been a while.
Wait, no.
So, Mr. Moore,
Yes.
what was that little argument that we had about, or not we, like me, you versus a truth with ionic compound, or no, you and a truth versus me about ionic bonds having, ionic compounds not being polar.
I don't remember.
It was like a 3-way war a couple of weeks ago. Well, the point is that we concluded that ionic compounds are not polar.
There's a continuum from covalent, from nonpolar covalent to ionic. As the difference in electronegativity goes up, the ionic character goes up. The molecule becomes more like an ionic, where the more electronegative one is pulling the electrons onto itself, the less nice they share. Even with an ionic bond, though, when the two ions are together, the metal still does have some claim on the electron, a little bit. So it's never purely ionic.
But then you said something about it not being polar at
But
all.
if you assume that we do have ions, there's sodium ions and there's chloride ions. What was your question?
You said that ionic compounds are not polar.
Oh, yeah, ions are attracted because one thing is positive, one thing is negative. It's an electrostatic attraction.
Uh-huh.
Not an attraction between something like this, where this has a positive side and a negative side. A chloride ion is negative all the way around it. It's a different kind of attraction.
Uh-huh.
Although it's the same. I mean, when water molecules attract one another, it's kind of an electrostatic attraction too. Well, I'm not arguing with you, Vinny.
Oh,
You're
okay.
looking for an argument, I'm not going to give it to you.
Oh. That breaks my heart.
That's what a truth is for.
Oh, okay.
So you should know that all the hydrocarbons that we learned about in organic chemistry, when you have just molecules with carbon and hydrogen in them, since the CH bond is not polar, that means that carbon and hydrogen have a similar attraction for the electrons. These do not mix well with water. Water tends to mix best with other polar things because of the interaction of charges. Non-polar things don't do well with charged things for that reason. Non-polar things will deal with other non-polar things, but those two are not compatible. Yes?
What do you mean by don't do well?
It means if I put octane into water, the octane will sit in a layer with the water underneath it in a layer. And if I shake that container, and it'll bubble and all that, and then eventually they'll layer out again. That's what I mean don't do well with. They won't mix together. They don't like each other. They repel one another, really. So they'll only touch each other at the interface where they don't have a choice. Okay, because gravity's pulling both down. The less density one is just going to sit on top of the more dense one. I said the less dense one will sit on top. Okay, now on the next slide I have several examples. Okay, how do we know whether molecules will be polar or not? This is probably the most confusing thing in the chapter. So try to focus. Now, in order to know whether molecules are polar, you have to be able to do dot structures, Lewis dot structures, and we've already done those now. And you have to know what the shape of the molecule is. So we did yesterday. So now that we've got those two down, now we can figure out if a molecule is polar. Oh, and you know what? Before we go to those, I just kind of jumped over this in the last slide. A molecule is polar if it has polar bonds in it that don't cancel out. Because sometimes you can have polar bonds in a molecule, but they'll cancel out so the whole molecule is non-polar. Well, that's what I'm talking about. It's confusing. Here's one example that I'll give to you before I even go to the examples page. Carbon dioxide. Are there polar bonds in CO2?
Yeah.
Yeah, because there's oxygen. Right? FON and Cl, you're looking for those. If you see FON or Cl in a bond, then it's a polar bond. Just assume that. All right. Now, if I made a model of CO2, it looks like that. We know it's linear. These are polar bonds. The oxygen's more electronegative, so the electron's yanking the electrons away from the carbon that way, and this one's yanking the electrons away from the carbon that way. They're pulling the electrons away at 180 degrees from each other. Is there one side of this molecule that's negative and one side that's positive? That's what the word polar means. Polar means that we have two opposite ends. Ends. The Earth is polar. You've got a north end and a south end, right? And all magnets, all bar magnets are polar too. There's two opposite ends to it. So this thing is linear, and because of that, we can't identify one side that's positive and one side that's negative. It's like since the electrons are being yanked away, it's like over here is negative and over here is negative, but that's not really what polar means. You can't have two negative ends. One's got to be positive, one's got to be negative. And that's kind of positive in the middle. So this is considered a non-polar compound. Even though it has polar bonds in it, they cancel each other out. It's almost like vectors canceling out. Those of you that have had physics, imagine polar bonds as vectors, where you have a vector going this way and a vector of the same magnitude going the opposite direction, 180 degrees, they just cancel out. You don't have one vector, one resultant vector, right? All of you have done vectors in math, right? When I say vector, you all know what I'm talking about. Yes?
So to find out like if electrons go to oversee the number, right?
You have to know the what?
Electronegativity.
No. Just know that if you have FON or NCl, one of those four things in a bond, then it'll be polar.
Yeah, but like actually like over the side.
FON and Cl are the highest electronegativity. The electrons will always be pulled to those four things. Yep, those are the high electronegativity ones. Yep. Here's many more examples. Oh, I'm going to just take them one by one. We'll do this one first. In the interest of time, I trust that you can do dot structures by now, and I'm just going to zip through the dot structures without really paying much attention, counting the electrons and all that. If you're weak in doing that, then practice over the weekend. So XeCl4 looks like this. Now, knowing what the shape is going to be already, I'm going to draw the dot structure like this. This is the Lewis dot structure for XeCl4. Are there polar bonds in this molecule?
No, yeah.
Sophie?
Yeah.
Yeah, because you have Cl in it, so there's polar bonds. Do they cancel out?
Yeah. Oh, well, to a certain extent, but now it's a seesaw.
What's the shape of the molecules?
Seesaw.
No and yes. Yeah.
Oh, never mind.
Square planar. Why? What's the coordination number on the Xe? Coordination number is 6, which means you're going to have an octahedral arrangement of the orbitals. But 2 of those are occupied by lone pairs. And so the angles are 90 degrees. Thanks for the smiley face, whoever put it in there. Is that you, Crocs?
You're welcome.
Well, she
Is that you?